So this is the summary from yesterday, effectively, that a geometric sequence is generated by this rule. This is the general term. U sub n is equal to U sub 1 multiplied by r to the power of n minus 1. Listen, it's not too challenging, I think, to understand where that general term comes from, right? Repeated multiplication from a first term. So I've just got an example here, and let me just erase that actually, because I'd like just to build it out rather than to show you the answer. Here is a problem where we need to find out what n is. So if you did your homework, you might have come across these already. I'm not sure. So a geometric sequence has a third term that is 50 and a sixth term that is 6,250. What is the 10th term? Now, in this instance, we are not told to find the general term. If we did, I'd probably just do that, but we're not. So we can use a logical approach instead, and this is what I'm suggesting you would do. I would personally do a logical approach, so I would do what I'm doing in slide 3, but I'm going to show you an analytical approach as well in case there are situations where the logical approach doesn't quite work. We know that to get from the third term to the sixth term, I'd have to multiply it by that common ratio r how many times? Yeah, it'd be 50 times, and for the video I'm just doing it on my fingers here, 50 times something times something times something will give me 6,250. Does that make sense? So effectively what I'm saying is that the sixth term will be the third term multiplied by r times r times r, which we know that we can summarize to just r cubed. Is that okay? All right, well, that's great because we know what U6 is, we're told it, 6250. We know what U3 is, we're told it, it's 50. So we can substitute those values in, and now we can solve for R. So I'll divide both sides by 50, and I will get, because I've done this before, this would be a calculator operation, but I already know what it is, 125 equals R cubed. And everybody knows that when you cube root 125, you get, well done Eve, 5. Just an FYI, just an FYI, on your graphics display calculator, if you are on the calculator page, if you need to work out what the cube root of 125 is, then I'm going to use this button up here, Control, and there's a little square root button. So Control, oh no, not the right one, the one next to it. Control in root X, put in the 3 here, put in 125 here, and press enter. That will get you the cube root of 125 if you didn't know it. I'd kind of expect you eventually, like what you should work on is knowing your squares up to 13 squared, your cubes up to 5 cubed, your power of 4 up to 2. You should know what 2 to the power of 4 is. Maybe 3 to the power of 4. And then powers of 5 onwards, maybe know what 2 to the power of 5 is, but anything else use your calculator for. That's kind of what I would expect, okay? So just, it's a memorization thing. So now that we've got r equals 5, I can say, therefore, u sub 10 is going to be is going to be u6 multiplied by what? Multiplied by 5, multiplied by 5, multiplied by 5, multiplied by 5. There's 4 more multiplies by 5 to get to the 10th term from the 6th term. Okay, you can't see it on the screen, sorry. So it's going to be U10 is equal to U6 times R to the power of 4. Am I making sense there? Uh-huh. Not too bad. which is 5. So I can go 5 to the power of 4. Okay? So that's going to be 6250 multiplied by 5 to the power of 4, which is equal to some big number. So again, on my calculator, I can go 6250 multiplied by 5 to the power of 4, press enter, and I get 3,906,250. So 3906250. Done. What do you think? That's the logical approach to the problem. Okay, it's the logical approach to the problem. I'll give you the analytical approach as well, just because it will be useful when it's not as straightforward as this. So the logical problem is, oh man, back to the screen. Please tell me if you see me writing and I don't flick the screens. I do forget a lot of the time. There we go. So that's what the answer would be. The analytical approach is basically saying if I have two terms that aren't next to each other, then I can do the following. It's kind of a similar, like it's almost like a simultaneous equations approach, but with multiplications instead of additions and subtractions. So the approach is like this. I know what U sub 6 looks like. U sub 6 looks like the first term multiplied by r to the power of 5. And I also know that equals 6250. U sub 3, I'm going to divide by U sub 3, and I know that looks like U sub 1r squared. And that is going to be over, I've been given the value of that, it's 50. So I end up with that equation there, this bit here. The one on the right here, this bit. Am I making sense so far? So I've used my understanding of the general term to come up with an expression here, and I've used the knowledge from the question to come up with an expression here. And the reason why I'm going to do that may start to be evident to you. Because these are all multiplications here, I can cancel out the U sub 1s. They're gone. Hooray! R to the power of 5 divided by R to the power of 2. Do you remember your index laws? If I've got a to the n over a to the m, it's a to the n minus m. Yep, so I just subtract the powers, in other words. So I'm left with r cubed is equal to, and then on your calculator, you could go 6250 divided by 50, and you'd get 125. And then I could use my calculator again to cube root 125 if you didn't know it, to get r is equal to 5. Then you could use the same logic to work out what the 10th term is. Or, if it's still not clear, I wouldn't do this, right? So I'm doing it for the notes, but I kind of wouldn't do this. You could go 50 is equal to U sub 1 multiplied by 5 squared. That's equal to 25 U sub 1. Therefore, U sub 1 is equal to 2. Therefore, U sub 10 is equal to 2 multiplied by 5 to the power of 9, which equals, fingers crossed, I'll do it on the calculator so you can sort of see it in action, but fingers crossed it gives me what I want. 2 multiplied by 5 to the power of 9, same number, 3,906,250. There you go. So that's how you'd use your calculator to do that. Now, warning. All of this is fairly straightforward and works because the terms were an odd number of terms apart. Oh man, got to go back to my screen. Okay, so whether it's by logic or by analysis, we ended up with r to an odd power. Yes? R cubed is an odd power. So when you do the root of an odd power, it's always either positive or negative. But if you take the root of an even power, it'll be plus or minus. So you've got to take that into account. If this happened to be R squared equals, say, 100, then R could be, with the information we've got, positive 10, or it could be negative 10. So remember, the size of R will generate the same number sequence, but if R is negative, it means every second number is positive, or every second number is negative, depending on how you see it. Okay, so if you've been given terms that are an even number apart, then you don't know whether the numbers in between were all positive or whether they alternated positive and negative. Okay, so basically at that point, if you ended up with with a square root or a fourth root or a sixth root or an eighth root, you have to conclude plus or minus that number, and then you have to basically come up with two solutions. The 10th number is either or, that kind of thing. Am I making sense? Do you have any questions? Speak now or forever hold your peace. Forever and ever and ever. Okay. So that's that. I've got one more example I want you to see. Just looking for my notes so I'm not speaking out of turn. Oh, actually, I've got two examples, actually. So here's an example that's worth going in, and I'm not too sure whether it's covered in the exercise already. What happens if we need to find n? So let's come up with a little bit of a scenario. So we'll make it a practical problem. When we're doing geometric sequences or exponential functions, we often have growth or decay problems if in a practical context. Either it's often population, and it's often about a population growing by a certain size, if R is bigger than 1, or shrinking if R is less than 1. Or if it's money, it's growing if you're getting more money if R is bigger than 1, or it's shrinking if R is less than 1. Absolute value of. So here's an example. Here's a practical example. So I'll just call it example. You can put it into your theory notes. I'll just put in brackets growth decay. Okay, a population of bacteria. Why not? Grow with the following data. That's really bad. That's real bad English, but you'll do. So on day 1, there were 5 bacteria. On day 2, there were 10 bacteria. On day 3, there were 20 bacteria, and so on. And the question is, when will the bacteria, or when will the population, I suppose, when will the population exceed 1 million? Okay, so this is an application problem. So the first thing we do is we look at it and we go, do I understand what it's asking of me? Do I understand every word there? Do I understand its impact? And do I understand what it's looking for? Some of them are fairly straightforward like this one, but it sometimes pays to really articulate what's going on here. So what are our variables? Number of days and population size. Yes, they're the two things that are changing. So when it says when will the population exceed 1 million, what am I looking for in terms of those variables? I can read that too, but in terms of those variables, what does when mean? Thank you, the number of days. Okay? As soon as you start articulating that, it gives you a sense of what you are looking for. I'm looking for a value for the number of days. Okay, cool. So what do? We're going to model it as a geometric sequence, and then we are going to solve that geometric sequence. So first of all, we are going to find u sub n. Look at the ratio first. R is equal to, we can pick any of those two consecutive terms and divide one by the other. So in this case, I'll just take the first two because the numbers are the smallest, and I get R is equal to 2. Is that okay? Mentally, you can pick two more and make sure it's still the case. 20 divided by 10 is 2. Yep, I haven't made a mistake. Or in the case of a practical problem like this, maybe it's not a geometric sequence. So checking a few values would be useful. In the real world, population would not be so beautifully even. So what you'd be doing in the real world is you'd have all these numbers and you'd be saying, do they seem to be growing by about the same rate is what you'd be looking for. And then you'd sort of approximate it from there. Okay, so we've got R. We know what U sub 1 is. U sub 1 is, of course, yep. So we can say, therefore, U sub n is equal to 5 multiplied by 2 to the power of n minus 1. We have our general term. What we're after is a population of 1 million. So which of the values there am I going to replace with the number 1 million? Go for it, Miles. So U sub n. So 1 million is equal to 5 multiplied by 2 to the power of n minus 1. What would I do next, team? Anyone can answer. Go for it. Not divide 5 by 2, no. You can't divide by 2. I'll explain why. 2 is contained here with an n to the power of n minus 1. If you remember your basic order of operations, what do you remember it as? Bed mass? Is that how you remember it? Or bid mass? Bod mass? Okay, O stands for order, but I'm going to get you to change your thinking a bit because it'll make more sense across the years. We're going to call it bed mass. The order, by the way, O for order is like a power. But we're going to change E in bed mass for the word exponent. So exponents have precedence over multiplication. So effectively, I cannot divide this 2 out because it is locked into the n minus 1 here because powers have precedence over multiplication. Exponents have precedence over multiplication. So you're not going to divide by 2. That's leaving your options a bit short. What else could you do? Divide both sides by 5. That gets rid of the 5 and leaves you with 2 to the power of n minus 1. And on the right-hand side, you've got 1 million divided by 5, which is? What is it? I don't know. 2,500, you reckon? 5 goes into 120 times, so yep. So, but again, you don't have to align that. You can certainly go 1, 1, 2, 3, 1, 2, 3. Is that enough zeros? It feels like it's too many. Divided by 5 is equal to 200,000. And here we have our issue, right? We have to work out what n could possibly be. Now, if you've done maths extended, some sort of maths methods class last year, you know that you can work it out using the opposite of an exponent, which is a log. Yeah, well done. But we haven't done logs this year, and guess what? I'm not expecting you to know or remember logs in order to solve this problem. Is that a relief? Number 2, what's another method you could use? Guess and check. Yeah. What do you reckon? What do you reckon? Wow. See, guess and check doesn't work if the first part you can't do. The good news is everyone has a brain big enough here to have a guess. Now, you might guess a billion. You think it might be 2 to the power of a billion minus 1. You'd be wrong, and oh my gosh, you'd be so wrong, your calculator will crash. But everyone here is capable of guessing a billion, aren't you? You could also guess 1. But if you think 2 to the power of 1 minus 1 equals 200,000, you know, we have more issues here than we need to deal with. So it's going to be somewhere. This is the good news. We have now limited it to somewhere between 1 and a billion. It's somewhere in there. Guess and check is literally pick a number you think might be right and then try it out. If it doesn't work, try another number. If it doesn't work, try another number. And all jokes aside, you're all clever enough to do that in a fairly quick fashion. Okay? But you don't have to do that either. And this is a thing I wanted to show you on the calculator because you'll need to use it with the homework assignment that I'm going to give to you at the end of this lesson. Your calculator, anyone who's used this calculator in previous years, your calculator, when set up in IB mode, is somewhat limited with its capacity to solve problems for you. However, it does allow you to do some solving. So when you open up your calculator and you go to the menu button here, and then you go to algebra, there will be just 3 functions that you are able to call upon. If you can see more than 3, it means that your calculator is not set up in IB mode. Okay, if you've got solve there, for example, or expand and factor, it means you need to turn that off because you can't get used to them throughout the next 2 years. You've got to turn that off. Just ask me and I'll show you how to if you don't know how to. What you do have as an IB student is numerical solve. So if I click on numerical solve and then I type my equation in, now I'll put in the one that we kind of half did, which was 200,000 equals 2 to the power of n minus 1. And then the other thing you have to do is press the arrow key and go comma and say what variable you're trying to solve for. In this case, it's n. So you type in n again, press return, and it will tell you, I'm just going to write it down, no, you can't see it, that it's 18.6. To 3 significant figures, 18.6 is what n is equal to. Okay? I could even, if I wanted to make sure that I wasn't making any mistakes, I could even go back to the initial one, which is a million, is equal to 5 multiplied by 2 to the power of n minus 1, comma n. Press return. That will solve it for you as well. So that's kind of cool, isn't it? Just write the equation. So your job is to form the equation. Your calculator's job is to create an answer. However, NSolve does have its limitations. Oh, yeah. The limitations are that it will only give you a single answer, even if multiple answers are possible. Now, when you're trying to find the value of n, that's okay. That doesn't really cause a problem because I think you'll only get one value for n anyway. However, if you've got, or it might give you n as a negative number, which you don't need. However, if you've got other solutions, then it may become a problem. So, for example, if I go n solve x squared equals 4, what's the answer to that? What should it be? Plus or minus 2. 2 solutions, right? 2 squared is 4, but so is negative 2. What I get from n solve is 2. I think, but I can't get this definitively, I think it gives the first positive answer. I think. But I'm not 100% sure on that one. It will tell you if there's no answer, that has no solution, right? There is no number I can square and get negative 4. If you don't understand why, ask. Okay, so it will give you some answers. There are other methods that you can use to get your calculator to give you more than one answer. I'm not going to show you, but I'll just tell you. Effectively, you do a graph, and then off the graph, you can read the information that you're looking for. That's basically how you do it. When it becomes relevant, I'll show you. In the homework assignment that I'm handing out, there are a few problems where there are actually multiple solutions. However, I'm only expecting you to get the one solution out of NSolve. If you notice that there would be more than one solution, make a note of it without finding it, and I'll give you extra credit for that because that would be really good. But you're not expected to find it. Is that okay, guys? Okay. We've got 30 minutes left in this lesson. I want to show you where we're headed. Oh, sorry, I haven't finished this problem off. Then we'll go next step. N equals 18.6. That's a dud answer. Why is that a dud answer, guys? Yeah. I mean, you kind of can, I suppose, but it doesn't really make sense in terms of a countable day. So often with a geometric sequence, we're looking for a whole number n. So in this case, what would I say? I would say, i.e., population will exceed 1 million by day 19. Okay. I would also accept this. The population will exceed 1 million during day 18. That would be okay, but you're assuming, which you would do for this, continuous data, right? Continuous growth, which is kind of what you'd expect. Unless, has anyone seen Gremlins? You know how like they turn, like if they're fed after midnight, that's when they turn into more gremlins. So they don't continually grow into more gremlins. It's only at midnight they turn into more gremlins. But anyway, so unless it was spontaneous growth at a particular moment in time, you'd expect there to be continuous growth. But of course, if we were actually modeling continuous growth properly, we wouldn't be using geometric sequences. We'd be using a function for continuous. That's by the by. We were using geometric sequences, so we would say by day 19. What if it said 18.1? What would my answer be? What's that, Izzy? Same thing, yeah. Even 18.1 would round in inverted commas to 19 because we could definitely say by day 18 it would not be a million. You'll only go to exceed a million by day 19. Okay, so context is king. You've got to make sure you get the context right. Alrighty, textbooks. Wrong one. Now, I have a problem with the textbook at this point. It hasn't said anything wrong, but I don't like what it's doing. It concentrates on basically growth and decay and also financial maths. In the growth and decay section, it talks about population growth models, radioactive decay as two examples of where we can use modeling. I have to say that basically when it comes to this sort of modeling, I'd almost always be using functions rather than geometric sequences. My issue, so we're now on page 114 if you want to follow through, is that it now starts to depart a little bit away from our usual geometric sequencing. It says we have an initial condition corresponding to time 0. This may be an initial investment or an initial population. We therefore allow a 0th term to begin the sequence. So you can see here that this is basically the same as the geometric sequence general form. Okay. We can talk about that individually rather than stopping the class right now. It's still not quite right in terms of what was going on there. Yeah. So it looks at an initial condition and then multiplies by r to the n, not r to the n minus 1. It is effectively just, I might do this on the whiteboard, so it's going to be missed in the video, but it is effectively just shifting everything down. So we've got usually u sub n for n equals 1 and onwards is equal to u sub 1 multiplied by r to the power of n minus 1. So it's basically shifting it downways by 1. So now u sub 1 is equal to 0. Sorry, now u sub 1 is going to be u0. And then to compensate for this shift down by 1, I'm going to have to add 1 to this, which gets me to n. That's basically what's happened. It's shifted down by 1 term, effectively. Okay, you're looking for the word initial, and that will be the situation. It works, don't get me wrong, but I probably wouldn't necessarily work like this normally. If I was starting to really look at initial conditions, I'd probably be saying, maybe I'll use an exponential function instead, where it makes more sense. So keep that in mind. Because we've done a bit of work around this already with a little growth problem I have, I'm not going to go through this example, but I want you to have a go at exercise 5D. I've got some particular exercises numbers from this I want you to do. So you can do that for the next 25 minutes. And in the next lesson, I want to introduce you to some financial maths as well, like compound interest and depreciation and stuff like that. So that's where we're headed in practical terms before moving on to exponential functions. Okay, so I don't have it in front of me what exercises you have to do, so I'll just stop the video and put it onto Google Classroom.